Right. So in the last class, we started double integrals, and there's a very important theorem by Fubini. It's called Fubini's theorem. So we can use single integral to evaluate a double integral. Okay. The definition of double integral is very similar to the definition of single integral, and we it's a limit of Riemann sums. But in general, it's quite it's almost impossible to use a limit and to evaluate integral. So we usually use iterative integrals, two single integrals to evaluate a double integral. So let's go over some problems here first. So let's take a look at the problem number 28. Right. So let's do number 28. Here's a double integral, and this is region, and here's y plus xy to the negative 2, and then dA. Okay, dA is just we call the area element. I equals from 0 to 2, and from 1 to 2. Okay, so let's do this problem. Okay, this is a double integral. Remember, right? And it could be any kind of functions here. So I think I did this problem before, but let me try and do this again. So first of all, double check. Is this function well-defined continuous on this region? Yes. The y variable cannot be negative, but it is between 1 and 2, so it's fine. Now, according to Fubini's theorem, you can evaluate using any of those iterated integrals. First of all, and it can be 0 to upper parenthesis here, and from 1 to 2, y plus xy to the negative 2, and dy and dx. Or it's from 1 to 2, you can interchange it from 0 to 2, and this is going to be y plus x to the, okay, using either of them. Okay, make sure the interval is corresponding to the dx corresponds to the interval for x, dy corresponds to the interval for the y variable. Okay, and then you decide which one you want to begin with. Okay, and for example, in this case, this is a doesn't matter, right? I can begin with the second one. If I use the second one, then you have to find the entire derivative of that function with y fixed. So y is a constant, so the entire derivative of that function will be in this form. It's from 0 to 2, and then dy, right? All right, so let's put plug 2 for x. I get 2y, and 2 square over 2 is just 2. And when you plug 0 for x, you get 0, so you only have one term. Okay. Then you only have function one variable. Then just by same idea, find the entire derivatives of this, negative, right? Negative y to the negative 1. When you differentiate that, I think I need a 2 here. Yeah, so I did not get 2 here, right? So it's a 2, then evaluate at the 2 endpoints. That's 2 squared minus 2 times 2 to the negative 1 minus 1 squared minus 2. Okay, and we calculate carefully. So what's the question? Right. So the first one is 4 minus 1 is 3. The second one is it's negative 1, so the answer is 4. Okay. So that is answer. Okay. Now, how to, this is the integral over over the rectangular region, right? X is from 0 to 2. This is 1 from 2. So it is going to be that region, right? And this is 1 to 2, right? 0 to 2. So we define the double integral over rectangular regions, close the rectangular regions. As long as the function is continuous, then we can apply Frobenius theorem to evaluate the integral. Now, what happens if the function is not defined on closed interval, on rectangular domain? Okay, so we can, if D be a closed bounded domain, an arbitrary, okay, in R2, for example, okay, and f x, a function defined on D, okay, and how do we define this integral? Okay. Well, we can the integral. Yeah, we're not going to talk about where the function is integral, but how to define. The definition is similar. Okay, still the limit of the Riemann sums, but we can use the formula to evaluate. Okay, the double int. So what I'm going to do is, so this is just like arbitrary D, right? It's in the back. So what I'm going to do is I'm going to use a rectangular domain, cover that, okay? And then I extend the function in the following way. If x and y is in D, okay? And here 0 if x and y are not in D, okay? And then outside D. Then everywhere else it's 0, okay? Then this double integral, right, of this function is defined to be this double integral over this regular rectangular domain, okay? And and this capital F is a function inside D. It's the same as little f of x, y, and outside D it's going to be 0. So this capital F is not a continuous function in general, okay? But we already know that we can define the double integral for general function, okay? It's not necessary to be continuous function, okay? So this is could be a general function, and that's a definition. You can call it a definition. You can also say that it's a theorem, because when you say the function double integral exists, means the limit of the Riemann sum exists. The idea is that you divide this domain D into many pieces. You only consider those small rectangles which has intersection with a D. Then you pick up the values, and then you consider the Riemann sums, okay? And you take the limit. That's the idea. So when the function is integrable, and you mathematics, you can prove that the integral on the left-hand side exists if only if the integral on the right-hand side exists. Although you know, in some cases, f is continuous, little fx continuous, but capital Fx is not continuous. It's just, you know, because it cannot be continuous, and because it's zero outside the domain and inside it's called f of x. So f of x is not necessarily be zero around the boundary. So the function itself, you know, can be dispersed. Okay? It can be broken. Okay. Now, using this, we can apply the Frobenius theorem again to solve the problem. Okay. So the question, yeah, here's the important fact. If fx is continuous, okay, on a D, then Frobenius theorem still holds for this double integral on the right hand side. So that means you can use the iterative integral to evaluate this double integral, okay? And when you can apply iterative integral, because you have the domain must be rectangle, otherwise you cannot write down the double integrals, okay? So this is the idea. Now let's how to solve the how to do that. Okay? Then it depends on the shape of the domain. Okay? Then you decide which iterative integral you can use. Okay? Sometimes you can use a vertical lines. Sometimes you can use a horizontal line. So let's go through. Let's do some problems. I'm not going to write down the formula right away. Okay. So here is an example. So from the example, you can see that. Okay. This is a double integral. Okay. And x plus 2y dA. Okay. And what is d? D is the region, right, bounded by y equals 2x and y equals 1 plus x squared. Right. So we have to draw the picture. Right. We have to draw the domain first. So this is a domain. Y equals 2x goes like this. Okay. Y equals 2x. And y equals 1 plus x squared goes like that. Okay. So there's intersection point, and this is a domain. Very strange, right? It's closed, bounded. Why we had to deal with this type of integral, double integral? That's possible, you know, if this is a piece of region, right, and like a material, and you know the temperature function at every point there's a temperature. Temperature is not constant, so you want to look at the average temperature, for example, later. So it involves the double integral over such a region. Okay, even the density could be different. So the integral of the density function gives the total total mass. Okay. All right. So how can I solve this problem? Okay, double integral. So we are going to use first of all, let's find the intersection points. Okay, 2x squared equals 1 plus x squared. So x squared equals 1, x equals plus and minus 1. And then the y value is going to be 1 plus 1, which is 2. Okay, so you have 2 points, 1 and 2, negative 1 and 2. Right? Okay, those are the 2 points. So it would be a good idea to use this rectangle to cover it. Okay, this is my region R. Right? This is a D. As this double integral, right, is going to be this this double integral over R, and here I have to use capital Fxy because this is going to be 0 outside of D, but inside D is going to be 2x plus 2y. Okay, so I can even write down this is okay for x, y in D, 0 for x, y outside D. Okay. So this is not a continuous function, but we still can apply forbidden theorem. Forbidden theorem says that original statement is for continuous function, but for this continuous function is still okay as long as it's continuous on a closed domain, okay, and bounded closed domain. If the domain is not terrible, consists of continuous curves, okay. So we're not going to go to details about the singularities here, but I guarantee the forbidden theorem still is true for this function. Now, once it's true for this function, then you can use a iterated integral to evaluate. So I think I'm going to put x outside and y inside. You can tell why, because it's easy to figure out the interval. And here from here, you see, x is from -1 to +1, right? Now, at the very beginning, I still use 0 to 2, okay? Capital f of x dy, okay? Got it? Yeah. But, as you can see that, this capital fxy for every fixed x, and this is going to be 0 outside the domain. So I can replace, if I want to replace capital Fx by x plus 2y, then I have to replace the interval. The interval right now, the lowest one, the y value, the smallest y value, right, is going to be 2x squared. The top one is x squared plus 1. Okay, why? Can you see that? Because the capital Fx is going to be 0. The reason is this capital Fx is going to be 0 for y greater than x squared plus 1 or y less than 2x squared. Okay, so that's why you don't need to worry about the 0 part. Okay, just focus on the interval from 2x squared to x squared plus 1. Here, x is fixed, okay, for every fixed x. So then you know, then you try to evaluate this. This is the integral with respect to y. So the antiderivative for fixed x will be x times y and y squared. Okay. All right. So now I'm going to put x squared plus 1 here, x squared plus 1 squared. Oh, that's too bad, too many terms. X, 2x squared minus 2x squared squared. You have too many terms like that. Okay. Then multiply this out. Okay. Multiply this out, you will get, let's see, x cubed plus x and x to the 4th, 2x squared plus 1 minus 2x cubed minus 4x to the 4th power. So I do have, let's begin with a constant. I have 1. How about x? I have a 1x. How about x squared? I have a 2x squared. How about x cubed? I have a negative x cubed. X to the 4th, 3x to the 4th dx. Okay. Another trick you have to pay attention is even functions, if an even function is integrate over interval from negative to positive, that be canceled out. So you really don't need to worry about those terms. Okay? Yeah, the integral of x cubed from negative to positive will be 0. Because this is other function. All you have to do is, I can even just put 0 to 1 here. 1 plus 2x squared minus 3x to the 4th. Right? That's the trick, okay? So that saves you time and also avoid mistakes. You don't need to evaluate the antiderivative at -1. For our even function, you just double the integral from 0 to 1. Right? So now you have an antiderivative. 2 over 3x cubed minus 3 over 5x to the 5th. Yeah, 0 to 1. Then all you have to do is just plug 1. Yeah. Then you simplify. Okay. Here's a note. Okay. If f of x is odd, that means f negative x equals negative fx. Then the integral from negative to positive a must be 0. Okay. Yeah. So if f of x is even, that means if you replace x by negative x, you still get positive x. Then this integral is going to be twice from 0 to a f of x here. Okay. So it's easy to understand from the picture. For example, like this. This is an even function, right? So the integral on the left-hand side is about area of the region. Area of the region is going to be double the area of the region on the right-hand side because it's symmetric, right? Yeah, these two sides, the region, those two sides are identical. Right, so now let's take a look at another problem. Another problem is going to be the double integral x and the dx. So what is the domain? Okay, D is the region, right? Bounded by the line bounded by line y equals x minus 1 and the parabola. Okay, so first of all, you have to sketch the graph for the D. Okay, you have to sketch it for the graph. Y equals x minus 1. So when x equals 0, y is going to be negative. So this is a line. Okay, and this y squared equals 2x plus 6. So that means x equals half of y squared minus 3, right? So this is a parabola opposite to the right and start from -3. So it goes like that. Okay. You still have to evaluate. Yeah, you have to figure out what type of iterative integral you're going to use, right? Yeah. I'm going to draw a rectangle. You know, it doesn't matter how big a rectangle you can choose. Maybe like this. Okay, this is that. As long as it covers the whole region. Okay, doesn't matter, right? But I have to find the intersection point. Okay, intersection points. So you how do I do that? Y equals x minus 1. So x minus 1 square equals 2x plus 6. Let's figure out x. So x squared minus 2x plus 1 equals 2x plus 6. X squared minus 4x minus 5 equals 0. And x minus 5, x plus 1. So I'll get two solutions. X equals 5, x equals negative 1. Yeah, look at this picture. It's reasonable, right? When x equals 5, the y value is going to be x minus 1, so it's 4. Here the y value is going to be x minus 1 to negative 2. So negative 1, negative 2, and here's 4 and the 5. No, 5 and 4. All right, so you got two points. And you can tell what is R, right? You can let R to be x is from negative 3 to 5, y is from negative 2 to 4, right? Yeah, this is R, but this R is a rectangle domain. It covers this irregular domain, right? Then your function, the capital fx, is going to be still x if x and y in D 0, if x, y all side D, right? All right, according to the double integral, the definition of the, right? This is going to be the double integral of R, capital fxy, and dx, okay? Now the integral, right? The all side D is 0f, so it does not make any contribution to the integral. You can think of this is a trivial formula. Let's accept it, okay? Then we apply forbidden theorem to this double integral. So the question is, x should be inside or y should be inside? You know, there are two possible integrals, right? And this can be, you have to decide if x is outside, then this will be inside. Or if this is a that would be dx and dy. Okay, so you have to decide which one you can use. There's no. Sometimes you can use both. Sometimes you can only use one of them. Okay, so it depends. If you use a y variable, a y variable is inside. You have to use the vertical lines. Okay, if you use the x variable, which is inside the x, yeah, then you have to use the horizontal lines. I think for this particular picture, okay, I think we should use a horizontal, yeah, horizontal lines. Okay, because it's easy to see that for any fixed y, then you can easily determine the range for the x. So any fixed y, for any fixed y, right? When y is fixed, right? So you can easily change that integral. Right? Here x is going to be you can solve it, right? X, what is x? Yeah, x is going to be y plus 1, and here x is going to be y squared. So let's go back. Yeah, y squared minus 6 divided by 2. So it's half of y squared minus 3. So for the fixed y, the x variable is between those two. Okay, so that's why you can, yeah. Okay, so I'm going to choose half of y squared minus 3, and that's y plus 1. Then over that interval for fixed y, the capital F of x, it can be replaced by x and the dx. Okay. Y is fixed for the integral inside. Y is fixed. So for fixed y, you can easily determine the domain for the x. Okay, so you replace the interval from -3 to 5, and 2, the interval depends on the y variable. Okay, and over that interval, I can replace capital F by x, origin function. All right, so now the antiderivative of the function x is going to be half of x squared, and then evaluate at 2 endpoints. Okay. So we get half of y plus 1 squared minus half of y squared minus 3 squared. Yeah, it's a little bit complicated, but this is a polynomial. You are able to evaluate the integral. All right. So let's multiply this. So I'm going to take 1/2 out. So I get y squared plus 2y plus 1 minus 1/4 of y to the 4th power. And this minus 3y squared plus 9 and dy. Okay. Continue. Yeah, let's list them in the order. Okay, y squared plus 3y, 4y squared, and plus 2y minus 8. Okay, then step by step, right? Then you find antiderivative of this. That will be negative. When the 5 is 20, y to the 5th plus 4 over 3y cubed plus y squared minus 8y, and evaluate those 2 points. It's complicated, yes. Okay. Now, if you make mistakes at this point, you only lose 1 point. Okay, 10 points out of 4. Okay, 1 out of 10 points. But you have to. The key part, if I give a credit, is this part. Okay, this is very important part. The rest of them just routine, just carefully do the computation, and this. So we know how to distribute the points for the whole solution. Okay, and at the end, you can put the number here. If you don't have a time, just leave it like that. Okay, and you come back late. Okay, this is gonna be -2 to the 5th plus 4/3 -2 cubed plus -2 squared minus 8 -2. So I'm going to leave it like that. I don't want it to the computation. So you can simplify it. Okay. So those 2 examples I showed to you is you only have a unique choice to choose the iterated integrals. Okay. Like for the second problem, the dx should be inside, dy should be outside. Okay. That because if I switch the order, you will see that I have to use a vertical lines. Then I have to have break the integral into two integrals because there's a trouble to describe the vertical interval for any given x. Yeah. It's not it's not easy to do that. Okay, so I'm going to find another problem which you can use ease of them. Yeah, so like a problem problem number 22. Okay, and D is the triangular region with vertices 0, 0, 1 and 1, 4 and 0. Okay, so let's draw the picture here. This is the 1 point. Here's another point, and this is okay. Now, of course, this triangle. You have to find the so the rectangular domain you're going to use should be this, right? This is the question is what variable should be inside. So the double integral is going to be the double integral over R. So this is a capital F x dx. If you use yeah, so let me write down all the two possible intervals. X is from 0 to 4, then this will be y is from 0 to 1. Okay, another one will be y is from 0 to 1, then x is from 0 to 4. I think either of them will work, but one of them will be more complicated. Okay, which one is more complicated? I think the second one is more complicated. Okay, for the first one, I have to replace capital Fx by capital Fx by y, right? So I have to use for the fixed x, I have to find the interval. Right? I have to find the interval for the y variable for the fixed x. Then it depends on the height of that point. Okay, I need the two equations for these two lines. The first equation is easy to figure out, right? And y equals x. The second equation, the slope is negative. Okay, the slope is negative. We have to do some computation to find the equation. Okay, what is a slope? Slope is the difference of y variable. It's going to be negative 1/3. Okay, so the equation will be passing through the point 4, 1 and 1. So y minus 1 equals x. Right? So that's the equation. Okay, so for the fixed x, the y value will be given by that formula. So we are going to use that integral, and this time for the fixed x, okay, for which y the point is still in the domain. For y from 0 to that 1 to the point on this line. So this line, the equation is y equals negative 1/3 x minus 1 plus 1. So that will be 1/3 x minus 1 plus 1. And over that interval, the capital Fx matches with the y value, right? Y. So it's dy and dx. Okay. All right. Now you find the antiderivative of that function, half of y squared, and evaluate at those two endpoints. And when you plug 0 for y, get 0. So all you have to do is just calculate this part. How can I simplify this? I think I'm going to use a substitution maybe. Yeah, that saves me time maybe. Okay. Otherwise, I have to use polynomials. Too complicated. I'm going to use substitution this time. Let u to be negative 1/3 x minus 1 plus 1. Okay. So when x equals 0, what is the y value? When x equals 0, y value is going to be 1/3 plus 1. It's going to be 4/3. Not too bad. When x equals 4, the answer u value could be 4 minus 1, 3 divided by 3, negative 1. It's going to be 0. Cool. Okay. So du equals negative 1/3 dx. Or dx equals negative 3 dy. Du, okay? So this above integral is going to be, when x equals 0, u is going to be 4/3. When x equals 4, u is 0. It's 1/2 u squared negative 3 du, okay? That saves you lots of time too, right? So negative sign can be used to rearrange the domain as the interval. So it could be 3/2, and here from 0 to 4/3, u squared du. Then the antiderivative of that is going to be u cubed, okay? And from 0 to 4/3, the answer will be just 4/3 cubed. So that is it, okay? Yeah, the substitution I think is good here to simplify my computation. Otherwise, I have so many terms. When you square, at least I have 3 terms: x squared, x, and the constant. So now I just only have 1 term, just u squared. Then I find the antiderivative. This triangle have a this triangle. There's still only unique way to find the evaluate unique way to use iterative integrals, unique order. But the next one, I'm going to modify the same double integral, but this time I'm going to draw the picture, just like that. Okay, here's 2, here's 1. How about this domain? I'm going to use either of them. I should get the same answer. Okay. So this is a D. So the equation, this will be the slope is negative 1/2. Then x minus 2. That's it. When x equals 0, I get a 1. When x equals 2, I get 0. So that's the equation for the strict line. Okay. So it depends on how they express it. You can also express as negative 2y, x equals negative 2y plus 2, I think. Yeah. Yeah, this is another way to describe the equation. Yeah, you multiply both sides by negative 2, then you move 2 to the left-hand side, so you get negative 2y plus 1. Yeah. All right. So this time, this is D, right? Now, R could be like that, right? Yeah. This could be that, the rectangle. So this will be that. And the capital F of xy, right? Capital F of xy is going to be y if xy is in the D, otherwise it is going to be 0. It is outside D. Okay. So first of all, it is going to be this. Then I can use any of the iterated integral. Here I'm going to apply forbidden theorem. There's two possible ways to describe the domain, right? Integral for x outside, then x is from 0 to 2, right? Then the y is going from 0 to 1. No, this is still capital F. Okay, or from 0, this is a dy. Then x is from 0 to 2. This is still capital Fx, right? All right, I'm going to change the interval for the first one, right? When x fixed, look at the picture. When x fixed, so the function f along this line, when y variable changes, x fixed, you get all the points on this vertical line. When you look at all the points along this vertical line, capital Fx will be 0 if y is greater than negative 1/2 of x minus 2. So this will be from 0, but upper bound for the y value will be negative 1/2 x minus 2. Okay, then you can change y by changing the f by y. Or from here, then you use the horizontal lines. Okay, if you use horizontal lines for the fixed y, okay, and for which x you still it's inside the domain. For x from 0 to the other one, it's negative 2y plus 2. Here's the y, here's dx, and then dy. Okay. Each of them, they look quite different right now, right? Sometimes they ask you to write down the other iterated integral for a given iterated integral. Okay. The reason I want to do this is because I want to do another type of problems later. Okay. So you're not given the domain precise at the very beginning. It's hidden in the iterated integral. Okay, you have to figure out the domain first. Suppose I give you the iterated integral on the left-hand side and ask you to write down the domain first, then interchange the dx and dy. That means I want you to get another one on the right-hand side. Okay? So using either of this, we're going to evaluate the integral. I'm going to call this I. This is the second integral. So the first integral, I'm going to get half of y squared, right? Right. So I will get negative 1/2 x minus 2 squared dx. Okay. So after simplifying, I get 1/8 from 0 to 2 x minus 2 squared dx. I think I can easily find the antiderivative of this. It's going to be 1/3 x minus 2 cubed. Okay. So let's evaluate this. That will be 8 and 1/3. When x equals 2, I think it's already 0. And when x equals 0, it's negative 2 cubed. Right? 0 minus, yeah. Plug 2 for x, you get 0. Plug 0 for x, you get negative 2 cubed. So this is going to be positive 8. So the answer is 1/3. Okay, the answer is going to be 1/3. Should be positive number. If why the integral must be positive? The domain is the first quadrant. The function y, right, is positive over that domain. Of course, the integral should be positive. So if you get negative, something's wrong. Okay, so that's the first one. The second one is going to be, let's see, where is this second integral? It's from, yeah, I forgot this, right? From 0 to negative 2y. Come on. See, I have a short memory. I cannot memorize this. Negative 2y plus 2. That's dx. Okay, dy. Okay. All right. So let's evaluate this integral. First of all, y is constant with respect to x. So just y and x. Right. Then you plug negative 2y for x, you get this. Then you find the antiderivative of that function. Okay, the antiderivative of this function is going to be negative 2/3 y cubed plus y squared. And evaluate. You will be surprised to get the same result, 1/3. Okay, this is a problem I show you using two different iterative integrals. You end up with the same answer. Okay, yeah, let's go over this problem quickly. This time you're given the domain, and you have a double integral, and it has dA there. Does not mean anything. Just okay, it's no x, no y. That's dA called, right? This is double integral, the standard notation for double integral. Okay, then you cover this domain D by a rectangle. So you change this double integral to a double integral over R. So I shouldn't put the y there. This should be f x dx. Okay, because the function is going to be 0 outside D. Okay, then I use iterative integrals for this double integral. The reason I can use that because right now the domain is a rectangle. Okay. Then use either of them. I evaluate the iterative integrals and I get the same answer. Okay. Okay. There are certain numbers of problems here ask you to sketch the region of the integration and change the order of integration. Okay, this is a problem number 48. Right? Sketch the region of integration and changes the order of integration. Okay, so it's from negative 2, from 0, 4 minus y squared, and f of x dx dy. I'm not asking to evaluate this integral. It's impossible. The function is not given. I wanted to put, I wanted to interchange these two. So you have to figure it out where it's from, right? It is from some double integral, okay? Right. So you have to figure out the D. Yeah, let's draw the picture here. How can I figure out the D? So look at this integral. This is actually, yeah, look at this integral, right? And clearly y variable is from -2 to +2. So y is from -2 to +2. Then for a fixed y, okay, the x variable is between 0 and 4 minus y squared. Okay, think about that, right? So now how do I describe it? Y is from -2 to +2. For any fixed y, x is between 0 and somewhere here. So I needed to find the relationship between x and y, right? So x is going to be, but this is also square, you know, x, yeah, let's look at x. What happens when x equals this, right? When you square it, so then you also get x squared plus y squared equals 4. This is going to be portion of the circle, right? Yeah. So this is going to be x and y. X is going to be 4 minus y squared. Okay. So now you get a domain D. Okay, this is a domain D. Okay, this is a domain D. Okay, you figured out this domain D. So here we actually use horizontal lines to evaluate the double integrals in some sense. Okay. So now you are going to exchange the order of the integration. So what I'm going to do is, I can use a rectangle here, right? That's R. Oops. Okay. So this integral is going to be the double integral of R and the capital F of X. Okay. And this time I'm going to exchange the order, right? So which one first? The dx first, right? Yeah, then the dy inside, because I'm going to interchange the order. So look at the picture here. X is going to be also from 0 to 2. Okay, no problem. But the y value, okay, and at this moment it's from -2 to +2. Okay, but I have to replace capital Fx by little fx. So I'm going to use, for the fixed x, I'm going to use this vertical line. Oops, I guess I learned over battery. I'm going to order new battery, okay. Yeah, sometimes it happens right now. It's like, all right, the pen is not working. Yeah, I think this time works. Yeah, good. All right, so for the fixed x, you have to determine the possible y values, right? For the upper bound and lower bound y value, okay? For the fixed x, what is the upper bound for the y value? Okay, you just solve the equation, right? And that equation is going to be 4 minus x squared from negative to positive. Yeah, right? You know, just solve the equation, solve this equation, solve for y. You get upper bound, lower bound. So now you can then you have to, then you put the little f of x here, dy and dx. For this kind of problems, you really have to understand the ideas. There's no unique formula you can memorize. Okay? You have to understand how to describe the domain. The domain is the middle, which is not given. Domain is there, it's given implicitly. It is not a, you know, it's hidden in the iterated integrals. Okay, you have to understand how to get the iterated integrals. Then you can understand how do we get to the domain. Yeah, then you get a domain. Once you get domain, you can exchange the order of the integration. Okay, otherwise, yeah, otherwise it's impossible. Okay. Okay, let's look at the problem. This problem. Okay. I'm going to interchange the order of the integration. Okay. Change the order of integration, and then evaluate if possible. Okay? If we have time, maybe I don't have time. All right. So this is the function. Okay. And if you evaluate this integral, it's very hard. Why? How do you deal with this part, right? It's integral with respect to y variable. It's complicated. Sometimes you are forced to exchange the order of the integration. Okay, so let's look at this. Based on what we are given, this integral x is from 0 to 1. So clearly x is from 0 to 1, right? First thing. Then for a fixed x, what is the y? The y variable changes from x squared to 1. Okay, so clear x is from 0 to 1. For every x, the upper bound for y value is going to be 1. The lower bound for y value will be x squared. So it goes like that. Okay, so this is a domain. Okay, yeah, this is y equals x squared. Got it? Yeah. Now, so I can use this one as my domain R, right? So this integral is going to be the double integral, first of all, is d, right? Double integral over the d. I still can write down the function like that. Okay. Now I can change it to R. Then I can freely use any of this iterated integral. Since you already have dx is outside, this time I have to put dy outside. Okay. Exchange it. So what is the y value? For the y value is from 0 to 1. Okay, and the x, I don't know. So I have to, right now x is still from 0 to 1. But this will be, yeah, I have to change this part. It's not going to be the function, it's going to be capital Fx. Okay. And then using the horizontal line, Okay, so let's see, what do we get? So for fixed, yeah, I have to write down something like that. So x variable, so y variable is between 0 and 1. Okay, but for every fixed, for fixed y, what is the lower bound for x, upper bound for x, right? X is less than or equal to 1, clear. But this one, the lower bound for x, I think you solve for that equation. Y equals x squared, so that's give me square 1, okay? Yeah. So now you get square y and the 1. For such x variable, you can still go back to, wait a minute, this is going to be, I'm confused. Okay, this is going to be dy and then dx right now, yes. Dy is outside, yeah. Yeah, dx, yeah. So dy is outside and dx is inside. The function is a square one of y. So, but this is a constant function, right? This is a constant function with respect to x. So the antiderivative will be just the square y sine y, and you put the x here, right? Okay. So you plug 1 for y, no, for 1 for x, you get square y sine y, then you plug square y for x. I think you get integrals like this. Okay, if we want to evaluate. Oh, I don't think I simplified. No, it's not simplified. Yeah. But this is this is the integral, okay? But we solve the problem, just changes the order of the integration. That's all we needed to do here. I'm trying to evaluate, but still you end up with complicated integrals. Okay, so we stop here, and we're gonna have a quiz maybe next.